Meeting. Alright, good morning, everyone. Let's just do a quick review of where we were yesterday, and then let's start looking at some practical implications of how the Q of the cavity affects the performance of the device. Uh, Basically, we had said that Q of the cavity is just a second. Q of the cavity is a good indicator of how strongly would the cavity store energy and thus how strong the resonance would be. And normally Q for these rectangular or microwave cavities is defined as the energy stored in the resonator divided by the energy which is dissipated or lost per cycle. So if you were going to define it in terms of time average power dissipated, then energy dissipated per cycle would be average power divided by frequency. That's the number of cycles we have within a second. And we basically have the Q of a cavity given by the equation here. This is going to be related to the resonance frequency and the bandwidth of the cavity. Uh, as we had looked at yesterday, the energy which is stored in the cavity is either stored in electric field, which we use WE, or the magnetic field WM. WE being half of epsilon magnitude E square in the volume, and Wm being half of mu magnitude of h square the volume. And not only that, we have seen that if electric field had a sine functionality, the magnetic field in that direction would have a cos functionality. So if I was looking at the cavity in one specific direction, let's say the electric field is having a sine functionality, and let's just assume that the mode is like that, and this is the electric field. The energy stored would be given by the square of that, so it would be basically be slightly thinner than this, and then going up, this would be WE, which is proportional to magnitude of E square. And for the same direction, if I was looking at the magnetic field would have a cos variation. So if the electric field has a sine variation, in that same direction the magnetic field has a cos variation. In its transverse direction, the magnetic field still would have the sine variation. So the magnetic field would have a cos variation and would thus behave something like that. And when it would behave, there should be there are two lobes, so there are two half wavelengths. So I should fix this part over here. The magnetic field would have two half wavelengths again. This area would be 1 by 4 lambda, this length would be 1 by 4 lambda, and this length would be half lambda for that specific mode. If I was going to plot the magnetic field energy is the square of that, so it's going to be something like this. That would be the magnetic field energy which is present. So what you notice is where the electric field energy is zero, the magnetic field energy is maximum. Where the electric field energy is maximum, the magnetic field energy is zero. So at these values, so if I was going to go and sit in the cavity over here, all the energy is going to be stored in the electric field. If I was sitting in the cavity right in the center, all that energy which is stored is going to be stored in the magnetic field. And these are standing waves which have been created inside, so they're not propagating forward. And we had seen that by seeing that the electric field and the transverse component of the magnetic field to it were always in quadrature phase with respect to each other in time. So what does Q, what does value of Q really represent? If I was going to draw the peak amplitude versus the frequency, so if I was going to draw the peak amplitude versus frequency, so this is omega, and normally we would do this as omega by resonance frequency, normalize it by the resonance frequency, so this would be 1, or omega here is omega r. And on the y-axis, I'm plotting the amplitude, a peak amplitude of a field. Energy or field, whichever one you want to pick up. If Q is small, then the variation would be something like that. So this would be something for Q is equal to 1. As Q increases, further away, the value remains roughly the same, but now the function becomes more narrower at the peak, and the peak value keeps on increasing. So this would be Q is equal to 10, for example. So as Q is increasing, peak value of energy density increases. If I go to slightly higher Q, then I would get a function which would be even narrower than Q is equal to 10, and would start to become more like a Lorentzian functions. So this would be Q, for example, equal to 100. The larger the value of Q, the peak value of the energy increases, and the delta F or delta omega, where I go down to 3 dB bandwidth, decreases. So if I look at the 3 dB bandwidth, I go to the peak and I go to half of the peak and I measure delta W, or with respect to Q is equal to 10, then the delta W, I pick up the peak, I will go to half of the peak, delta W, versus over here where delta W would be something like that. So the bandwidth of this resonance function starts to keep on decreasing the larger the value of Q. Again, these cavities are used to store energy, or these cavities are used to make filters. So you want your resonance to be high. You want your resonance effect to be large, and thus you normally want to operate it as at high values of Qs. Let's let's do some simple calculations and let's try to understand where do we land when we make the Qs with these cavities. We had seen that, again, remember, we had calculated Q for TE101 mode And this was assuming C is greater than A is greater than B. So this is the dominant mode for that specific cavity. So we had looked at Q is 101. This Q101 we had seen was given by gamma F101 mu naught ABD A square plus D square by RS to be A cube plus D cube plus actually we were using C dot D, so let me change that. C cube plus AC A square plus C square. The first question which arises is why do we choose the TE mode? Why do we like the TE mode? And remember again when we were calculating the losses in the parallel plate waveguide, we had seen that the loss for the TM mode is going to be larger than the loss for the TE mode. Again, the TM modes, which have lot stronger magnetic fields, which are parallel to the parallel plates, to the conducting plates, the TM modes have stronger H terms parallel to the conductors as opposed to TE, mode. So the TM modes have lot stronger H terms, and thus the surface currents in TM modes is larger, and thus loss in TM modes is larger. And Q totally depends on the loss within the cavity. The smaller the loss, the higher the value of QB. So TM modes normally have higher losses than TE modes. We saw that in parallel plate waveguides. We saw that in rectangular waveguides. And the reason basically is coming from the fact that you have much stronger H parallel feeds to the conductors, which builds up this loss. So it's always advantageous to try to work within the TE mode applications, especially when we want to achieve higher Q terms. We want to reduce the loss as much as possible. The second question which arises is why only use dominant modes? Normally, these cavities are designed only to operate within the dominant mode. And the reason again we have seen that as mode order increases, energy is pushed from the center towards the sides. Towards the conducting walls. We had seen that for the first order mode, the energy peak is right in the center of the waveguide, and it goes it becomes lower as you go further up. So most of the electric field, magnetic field intensities are right in the center. Whereas as you increase, go to the higher order modes, the energy is being pushed towards the side. The center for some of the modes doesn't even have any energy. The energy is being pushed towards the sides, so that therefore the field interaction with the metal becomes larger. Therefore, you increase the surface currents. Therefore, the loss is always going to be higher. So loss for higher order modes at same frequency is going to be larger. Is always normally is always going to be larger because that energy has been pushed towards the conducting regions. So thus, when we are going for high Q cavities, we always like to operate in the dominant mode. We always like to excite the dominant mode within these cavities. The third question which now arises is, yes, we have Q101 or TE101 which we have chosen to create low loss. So create the lowest possible loss. And the question next arises is, well, we have done this calculation for a cavity which was arbitrarily chosen, dimensions of A, B, and C. The question which arises is, what values or what relations between A, B, and C would give the highest Q? For a given conductor. What should be the relationship between A, B, and C's which gives you the highest Q? Remember when we were doing rectangular waveguides, we had said B is equal to half of A was a good place because at that place you basically get enough bandwidth that the second order mode doesn't show up. Your operating frequency bandwidth is decently large, and then the loss is actually lower. As B approaches the value of A, the loss starts to increase a bit in rectangular waveguides. In this case, what we are doing, this case is slightly different. In this case, what we are doing, we are storing energy in the volume given by A, B, C. We're storing energy in this volume enclosed within this cavity, and the loss is coming. Where the loss is coming from? The loss is coming from the surface area of the conductors. And going back to your high school maths, literally from the term of dimensions, what we want to do, we want to store this energy in the largest possible volume with the smallest possible surface area. We want to achieve the volume we want with the smallest possible surface area within this geometry. And going back to your high school physics or high school maths, you know that for a rectangle, smallest surface area is achieved, smallest surface area for the same volume is achieved for a cube within the rectangular aspects. Later on, we will look at a cylindrical cavity where the surface area would be even smaller. A circle has smaller surface area or smallest perimeter compared to a square, but the square has the smallest perimeter with respect to the area compared to a rectangle. So this, for the same volume, the smallest surface area I can achieve is for a cube. So for most practical purposes where we want high Q, we want to reduce the loss, A has to be equal to B has to be equal to C. This is the case where we use for most practical purposes, we go for cubes as possible. If I have A is equal to B is equal to C, then my Q101, we can substitute the values in there. This becomes pi F101 mu naught A. Instead of B, I have A. Instead of C, I have A. A cube plus A cube divided by RS 2A A cube plus A cube plus A square plus A square. And if you just play around with the terms, you will see that this will turn out to be pi F101 mu naught A by 3 RS. So we had started with a horrible looking term, but for most practical purposes where we are going for cube looking cavities, and in fact later on we'll see it's actually easier to do a cylindrical cavity. For most practical purposes, this is what is going to happen, and the cube is not that difficult, and this is true for cubic cavities. So again, we are going for the cubic cavity because I get the smallest surface area for the same volume as opposed to a rectangular cavity. And the smaller the surface area, I would get lower loss because ultimately your current is being integrated over that surface area. So for this, I would get the lowest loss, and if I have lower loss, I would get the highest value of Q I can achieve. Any questions so far before we put numbers to this? You have any questions?
No questions here, sir. Sir, we can't hear you. Sir, we can't hear you.
மஞ்சு மேம், மஞ்சு மேடம்,
கேக்கல.
மேடம் இது சொல்லிட்டீங்களா சார்கிட்ட ஆடியோ கேட்கலன்னு?
கேக்கலன்னு சொல்லிட்டாரு. அவருக்கு கேட்க மாட்டேங்குதுன்னு நினைக்கிறேன்.
சரி, ஓகே. மேம் ஒன்றும் இல்லை, இப்போ லாக் அவுட் பண்ணா கண்டிப்பா அவர் ரெஸ்பான்ஸ் பண்ணுவார். லாக் அவுட் பண்ணிட்டு மறுபடியும் லாகின் பண்ணிடலாமா? ஏன்னா அவர் சைடு ஆடியோ இல்ல, அவர் சைடு ஆடியோ மியூட்ல இருக்குன்னா நம்ம பேசுறது எப்படியா அவர் ரிசீவ் பண்ணணும் இல்ல?
அதான் chat பண்ணான்னு இந்த chat ஓபன் ஆகல.
சாட் ஓபன் ஆகலைங்களா?
ஆஹா.
சரிங்க மேடம்ப்பா.
Sir, we can't hear you.
மேம் லாக் அவுட் பண்ணிட்டு மறுபடியும் லாகின் பண்ணிடலாம் மேம். அப்பதான் ஒரு மறுபடியும் செட்டப் பாப்பாரு.
பண்ணுங்க.
பண்ணிடலாங்களா? லாக் அவுட் பண்ணலாமா? யா, ஓகே.